This video, I'm just going to go through some of the documentation that I found that helped me to create the schematic for the monoblock amp. This first drawing is a design called the Howler Monkey, designed by G. Forrest Cook in October 2015. From this, I took some design concept ideas for the phase inverter and for the push-pull 6KQ5 outputs. Mainly what I was interested in here was his usage of a constant current source for the long tail differential pair forming the phase inverter. Notice that the design is a phase inverter, not a phase splitter, and I'll go into the differences between the two in the next document. So we have the volume here from the previous stage. It comes into this would be the, I guess we would call it the positive input, and then the 180-degree output captured on the cathode, or the plate, would be coming out here. And then this is the dropping resistor for the B+. The other phase is on the top here, and its input is for the most part grounded, although he did use it as the feedback path from the output amp to reduce some of the open loop gain. This is something I'll explore later on in my design. From that, I can get some idea of what values of resistors and capacitors he was using in his design. This is a nice little document. It's called All About Audio Amplifiers, and it goes through a couple of the designs that were used, as well as showing some of the linearity of them in terms of THD measurements. This first one is an inverter circuit. And then we have a closed loop phase inverter. These are not long-tailed pair designs, though. This is the first long-tailed pair design, and it's denoted in this schematic by a common cathode with one path to ground. This forms a common current source shared between the two tubes, or the two parts of the tube, the two triodes. And the difference is that let's get into, in both of these, the term phase inverter is used for something like a long-tailed pair differential stage. This is another shot of the long-tailed pair, more traditionally drawn in the way that a more modern design using transistors would be drawn. You can see here in the vertical orientation the tail, the common tail, with the in this case I drew in a constant current source to replace the 470 ohm resistor, and then on the plate sides we pull off the output signals. So this side here would be a signal coming in. The other side is essentially clamped to ground in terms of the AC, and in terms of the DC it's biased to this point in the tail equally with this one here. The other design for a circuit that gives you the 0 degree and 180 degree signal It's called a phase splitter, and you see this on other circuits. I've seen this in, for example, tube amplifiers, where the outputs are actually taken from both the top and the bottom of one triode only. In this case, the voltage drops across the upper and lower voltage divider resistors. You want to keep those matched, because the goal of a phase inverter or phase splitter is to have 0 degree and 180 degree outputs, but they should match in amplitude to one another. So from the notes on this one, I use this as the design for my amp. I then went to the Brimer 12AU7 application report, and this was something that was created in 1950 and reprinted in 1952. I used this to get the triode curves for biasing at different grid voltages, and then along the horizontal axis you have the plate voltage, and on the vertical axis you have the current through the tube. So I took a look at 5 and 2.5 milliamp bias lines, and what would happen if I would hold the current through the tube at 2.5 amps. You can see I can get a nice balanced output here if I use about -5 for the grid bias. So this is a sketch I made of the phase inverter. I was trying to figure out where my bias points would be in the circuit. Going back to the chart, at a -5 volt grid bias, we're looking at about 130 volts for the plate voltage. So we would know that across the triode we're sitting at about 130 volts. This is given 2.5 milliamps going through each leg for a total of 5 milliamps. So if we set the constant current source to 5 milliamps, which we can do with this simple circuit here using an LM317 regulator, we can then determine the values of R105, R102. I set the bias of R102 to drop about 5 volts across, and from that we can determine that it should be 1K. We know that the voltage drop across the constant current source is another 4 volts or 5 volts, because that's where we are at our bias point 5. So we have a total of 10 volts between the ground and the cathode. If we use a 200 volt B+, we're now looking at 190 volts for the remainder of this. If this is going to be at 120 volts, we have, let's say 80? Let's say 80 volts of remaining voltage drop to account for. If we take a look at R103, we want to get it close to 80 volts on that. If we set it to 33K at 2.5 milliamps gives us a voltage drop of 82.5 volts, which is pretty close to where we are in terms of the 80 volt reserve. So now, using those values, we can fill in both sides of the long tail pair, and then the R100 and R101 are just large values like 470K. I'm just using 0.1 microfarad capacitors across the board for all my decoupling. I used this application report from Texas Instruments. It's SLOA 4042, and it's talking about a TLC 074 op amp. I'm going to be using TL series op amps, close enough. In this we can see there an example of a bass and treble boost cut circuit. These are interesting circuits because they can both amplify and attenuate a band pass part of the spectrum. An example of that here is in this frequency response here, where you can see on the low pass side, the bass side, you can both amplify the low frequency response as well as attenuate the low frequency response. And in the middle of the setting, we just have a flat response. This is the treble part. We don't really need the treble part because this is a bass amp. So in my designs, I went ahead and removed this part of the circuit. This is the sketch I made for the main circuit. Right here we see the input section, the preamp, which has the left and right audio input as well as the pass-through. Missing in the schematic is something I have to add in. I moved the volume control to the front here to allow me to just set the voltage input right at the beginning so that nothing saturates down the line if the line voltage is too high. I use buffers here to avoid mixing the left and right channels, because you have to remember that on these ports here connect to the downstream main amplifier, and I want to keep the left and right channels nicely separated. These are just plus 6 dB amplifiers, or times 2. They feed into a summing circuit, which is actually a negative gain summing circuit. It doesn't really matter. I'm just flipping the phase back and forth, but in terms of the phase only really matters when you get to the latter half of the design. This part of the circuit is a passive low pass filter. This is the active low pass filter, the bass boost cut. It uses the design from the application note I showed previously, and it uses an active feedback path to allow this thing to both have a gain as well as an attenuation. This design is actually kind of interesting, and it's fun to go through it and actually figure out how it works. I might do a separate video on that to talk about how that works. This is the passive low pass filter. Initially I had it set to have a 3 dB cutoff point at around 400 Hertz. I'll probably mess around with that a little bit to fine tune it. I can change the capacitor up and down to change the crossover point. The final op amp is the buffer going to the phase inverter, and it just provides a fixed gain, which I then use the trimmer to cut it down such that it doesn't oversaturate the output stage when you're at full boost on a line input. The power supply is pretty straightforward. We have two transformers supplying the high voltage and low voltage sections. In a previous episode I showed you the two transformers that I was going to use. I don't think I showed the low voltage transformer. It's just a standard Hammond transistor. I think it is I have it here. It's a 161E16, but that particular number is no longer available. The 161E series or the 161E, I guess you could say 161 16 series is still available in other forms. It's a dual secondary tap, or separate secondaries, and they provide about 16 volts AC. The larger power transformer has dual primaries, and they're put together in parallel to for proper voltage set up on the primary side, which is 120 to 125 volts AC. The high voltage tap secondary, I'm using just a standard dual diode stage here to get a 120 hertz rectified signal coming off the transformer. It goes through a ballast resistor to minimize the current surge when it's first turned on and the filter capacitors start charging. This is a standard pi network filter, so we have a capacitor, choke capacitor to provide optimal filtering. I've added a smaller 0.1 here to get rid of some of the noise. R2 and R3 are the resistor divider network to get the two high voltage B plus and B plus plus. I am tentatively setting B plus to be around 270 volts, B plus plus at 200 volts DC. Going back to the low voltage system, it uses two full bridge rectifiers and two paths to give me regulated positive 12 and negative 12 volts DC using 78 L12 and 79 L12 linear regulators. Using the L series for low dropout to get close to the unregulated input, which I think is hovering around 15 volts. The other part of the high voltage is supplying the filament voltage, and that's just 6.3 volts. There is a center tap on the transformer. I'm not going to use it. I'm going to create my own virtual ground, and that way I can more accurately tune out the noise, or what's called the hum balance. And this is the hum balance circuit I'm going to be using. So it just takes the two sides of the 6.3 volts, runs it through a voltage divider, and this is a trim pot that I can use to set the ground point bias here to minimize the hum noise coming from the filaments. This is the final part of the schematic. It shows the phase inverter coupled into the 4-tube output push-pull output phase stage, and all of the passives surrounding that. This is the output transformer that we've seen in a previous episode. It has 40% screen taps on the primary, so those feed back into the tubes, the upper and lower tubes, through 1K resistors to provide a little bit of separation between tubes for screen biasing. I may mess around with this and see if this works better, or a constant DC voltage works better for biasing the screens. That's something I can play around with. So that's basically it. I guess the wrap up would be just to take another look at the constant current source. That was similarly explained in the other schematic I used for determining resistor values for this. Just as I said before, it's just a 317 linear regulator, and there's a formula that you can use for these. Let's see if I can find it. Yeah, the formula here is this one here, where I is approximately 1.25 divided by R1. R1 is the resistor separating the voltage input point from the adjust point. Sorry, this is the output of the regulator. So there's an output of the regulator that goes through a dropping resistor, and then the other side of the dropping resistor is used to for the adjustment voltage of the 317. So for example, for 10 milliamps, the resistor would be 125 ohms. And in our case, we want 5 milliamps, so the resistor would be 250 ohms. This is the subplate that I came up with for the amplifier. As we talked about in a previous episode, this is the plate that sits just under the surface of the chassis on the top side, and it's used to hold all of the sockets for the tubes. These two pieces on the side will be tapped and threaded into the side of the chassis, and it'll use this to hold it securely to the inside of the chassis. So there's no holes in the top of the chassis other than the ones needed to have the tubes poked through. The holes surrounding each of the sockets is designed for a couple of purposes. The first one is for airflow. It allows air to come up through the tubes, or between the tube and the top plate of the chassis. There's going to be a larger hole in the chassis, larger than the diameter of the tube, that allows airflow to come up between the outside of the tube wall and the outer circle describing the hole in the upper chassis. This is a bottom view of it. I've already started putting in terminal strips for the different tie points for the passives. I use a common ground bus bar in the circuit to give me a good solid ground, and I like to use star ground points in my amplifiers, so this will go back to the star point, or the source point for the ground for the entire amplifier, and this becomes just one branch of the grounding star. This is where the heater is going to be coming in, and I'm going to try to minimize noise generated from the heater voltage wires by having them go through this hole here to the top of the chassis, and then route the wires on the top side of the plate to the appropriate places near the sockets, and then use these holes to have the wires go down and then tie into the socket on that side. In this way, I'm trying to separate the 6.3 volt AC line from the rest of the circuit, doing the audio to try and minimize noise. When I'm doing this, I also have to consider how the tie points will be used. So what I come up with is a sketch of the layout of the tie points. Actually might work better. Let's see if we can bring it in here. It's going to be hard to get into the shot, but that's close. So you can see here the ground wire, this from the star point, and then all the resistors and capacitors from the circuit. I determine where they're going to be laid out on the point-to-point wiring, so I have a pretty good idea of how to actually wire the circuit. And this gives me an idea of if I have enough tie points or not, if I'm going to be running any problems with long lead lengths for components. This is somewhat exaggerated. You can see it's much shorter here, so I don't think this will be a problem for the resistors to stretch. I also needed to find a place for the constant current source, so I put that in here. It requires 3 tie points, one of them being ground. So I just have the ground here, the resistor, and then there's going to be, let's see now. No, I stand corrected. The constant current source really only needs 2 tie points, not 3. Because the adjustment leg is actually tied to an existing resistor that is on the output facing up towards the cathodes of the phase inverter. For the high voltage point-to-point circuitry, I decided to create another plate that would go inside of the chassis, and this plate is directly underneath the 2 transformers on the inside of the chassis, like so. So the power transformer and the output transformer on the top of the chassis would bolt down to this subplate. It serves a couple of purposes. It stiffens up the upper surface of the chassis a little bit. It means I don't have to worry about nuts and bolts in securing the transformers down, because the plate has threaded inserts already press fitted into it, so they're secured. To do this, I made some measurements and I drew a sketch up of where things should be, where all the holes are for the wires coming down out of the transformers. And then I determined tie points, tie strip points that I could use to create the high voltage circuit. From this, I created another point-to-point sketch showing me where all the resistor, diode, and capacitor and choke tie points would be that I would take advantage of in the circuit here. So there's no surprises. I know where everything goes. I know what all the tie points are being used for, and it's harder to make mistakes that way. So that's just an overview of what I've got so far in terms of the design, and also some of the mechanical parts that I've made to date for the amplifier. I haven't yet drilled any holes in the chassis. I'm going to try and leave that to a final step. What I will do is I will prototype the amplifier, get it up, powered up and running with everything laid out on these plates. So all of them, they would all be wired up and interconnected, and that way I can test the circuit and make sure there's no surprises before I actually put it in the chassis. I can also use that opportunity to do the final positioning for the choke and the low voltage power supply inside of the chassis, and also the power switch and the fuse, not the fuse, but the RCA jacks for the input and the pass-through. The volume control and bass boost cut is already designed, and I'll show that in the next video what I did for that circuit. Both the low voltage power supply and the preamp and filter stages are going to be on PC boards. That just allows me to cram all of this into that smaller chassis. Trying to do this with point-to-point wiring would be really difficult, and I think the PC board seems to be the best compromise. I'll try to get the next video out within the next week or so, maybe sooner, depending on my schedule. I'm a little busy right now with work, so I try to do this stuff as time permits. So until the next episode, I hope everybody's doing okay, and take care now.